Hello, I'm Linyi, and I'm glad to introduce our paper, Planar Surface Reconstruction from Sparse Views. This is a joint work with Shengyi Qian, Andrew Owens, and David Fouhey. Consider the two photos of a room. There is a chair on one side, a bedside table on the other, and a large glass wall and floor in the middle. They are taken from very different camera poses, and very little of the scene structure within them overlaps. Despite these challenges, we can still understand spaces like these from a few ordinary photos. The goal of our paper is to give the same ability to computers. Given two RGB images with unknown relationship, we want a single and coherent reconstruction. Our system needs to output a set of planes and the relative camera pose of the input images. Here is a sample output of our system rendered in different camera views. Previously, many works aimed to find correspondences between regions of images. However, pixel-wise correspondences only work on overlapping regions, and most of the area in this scene, for example, isn't overlapping. There is no information in the non-overlapping regions to reconstruct. Meanwhile, there exist many works to map 2D images to 3D structures. Planar RCN, for example, uses a deep neural network to detect and reconstruct piecewise planar surfaces from a single RGB image. In this example, Planar RCN does a good job of extracting different planar regions in each image. However, we still don't know how to put things together. For example, we will have two pieces of the same glass wall from the two input images, and we need to know how to stick them together to produce a coherent output. In general, single-view reconstruction systems like Planar RCN will produce multiple slices of the same object if it appears across views. As we need one coherent reconstruction instead of a simple mixture of per-view segments, grouping within the overlap region is important. The relationship between reconstruction, correspondence, and camera pose has long been well understood in the multi-view 3D community. Our work is different from NERF, which generally works on one single scene and requires camera pose as input. Our work predicts camera poses and generalizes to novel scenes. While we use two well-separated and unknown views, our approach is different compared to standard two-view stereo or visual SLAM and more similar to white baseline stereo. And unlike white baseline stereo systems, we also need to produce reconstructions for portions of the scene that are seen in only one camera. The most similar work in this direction is associative 3D. Here we reconstruct volumetric objects using multiple networks and a heuristic ransack-like optimization from two images. While effective on a 6-object subset of a synthetic dataset, these components fall short on the more challenging realistic multiple 3D dataset that our work uses. By contrast, we propose a more principled optimization strategy to handle planar segments in realistic data. Additionally, our approach has one backbone network forward pass per image pair. Our insight is that the three related challenges, per-view reconstruction, inter-view correspondence, and the inter-view camera pose, should be jointly tackled. We adopt Planar RCN to estimate per-view reconstruction, while jointly estimate correspondences and camera pose. Now let's get into the details of our work. The input to our system is two images. The system produces backbone features using ResNet 50 FPN. Following Planar RCN, we use a region proposal network to propose boxes and then infer plane masks and parameters from the ROI aligned features. We additionally predict an embedding vector for each plane, which serves as an appearance feature to compare the similarity of surface texture across views. Our camera pose module estimates a distribution over the relative camera pose between views. This enables joint reasoning between a holistic estimate of the camera, as well as valuable cues in the estimated geometry. We attend the P3 feature from the same backbone to capture similarity between images at each pixel in a feature map. After that, we use a convolutional and linear layers to predict the camera distribution. We find this attention to be superior compared to the strategy of concatenating average pooled vector outputs, as in prior works. So far, we've introduced how we predict planar surfaces, correspondences, and camera poses from a single network. However, we are not done since the network may not predict the optimal solution directly. We need an optimization step to produce the final output to jointly reason over correspondence and cameras. Suppose our network predicts m planes from the left image and n planes from the right image. Each plane has a plane parameter and an appearance feature. We also predict the cross-view camera distribution over k-beams. We first solve a discrete problem that selects a camera from the k options and the plane correspondence matrix C. Assuming camera k has been selected, we can find the match matrix based on the score matrix for this camera. The score matrix is an m by n matrix, encoding the quality of a plane correspondence. Based on the score, we can use Hungarian algorithm to find the final match matrix. Each entry of the score matrix jointly considers the 2D appearance distance in the blue box and the 3D geometry distance in the red box, and link the two by weighted addition. The sum of them are 0 with perfect matches. The overall objective function contains the match cost, which is the dot product between the score matrix and the match matrix. We also combine it with two regularizing terms. One rewards matching objects, and the other penalizes unlikely cameras. The terms in the blue box is solved per camera by the Hungarian algorithm, and the red term is a scalar per camera. The overall objective function is minimized over a set of Hungarian algorithm problems. We pick the best correspondence and camera that optimize the objective function, which encourages selecting a likely camera, as many planes as possible, and correspondence that is consistent in both appearance and geometry. Having selected the best camera bin and planar correspondences, we use nonlinear optimization to continuously refine the camera and the plane parameters based on the pixel-wise correspondences to produce our final reconstruction. We generate a dataset specific for this task. We fit ground truth planes on multiple 3D mesh using semantic labels to constrain the planes. We sample camera pairs to contain sparse views with an average of 21% overlap in each camera pair. Here we qualitatively show some reconstruction results on the test set. We show our reconstruction from two novel views. The blue and red frustrums show cameras for image 1 and 2. Here is another example, where the cameras are facing each other to capture both sides of the bed. Our system can recover large areas of the room just from two views with a large viewpoint change. Here is a reconstruction of a kitchen, and we compare our reconstruction on the bottom left with the ground truth on the bottom right. We compare with alternative approaches and ablations that test the system's contributions. To the best of our knowledge, no existing work solves our task, so we test the fusions of existing systems. There are two components in the baselines: plane reconstruction and camera estimations. We use plane RCNN or Manhattan World Stereo for plane reconstruction, and RGBD plane odometry, superglue, or our modified RPNet for camera estimations. We first show a qualitative comparison of this image pair as input. Manhattan World Stereo plus RGBD odometry fails on this thing even with additional ground truth steps as input, because they mainly uses geometry and is designed to work on large overlap image pairs. Plane RCN plus superglue can have a reasonable reconstruction given the ground truth camera translation scale, but they fail to merge the walls together across views. Our method predicts accurate camera poses from the inputs, merges planes across different views, and aligns their textures to produce a coherent reconstruction. And here we show the ground truth. Next, we show qualitative evaluation. We treat the full problem as a detection task and evaluate using average precision. We define a true positive as a detection satisfying three criteria, including mask IOU, surface normal distance, and offset distance. Plane odometry finds pose primarily with plane normals. Its correspondence is often wrong because our low overlap setting limits the information in geometric cues alone. Superglue or APINet with plain RCN outperforms plain odometry by using deep features to find correspondences or camera poses. Our proposed approach further outperforms all the other baselines by a large margin in AP because it eliminates duplicate copies of planes and reduces inconsistency between predictions. Next, we evaluate how well we estimate the relative camera poses. Due to limited information available in geometry alone, plain odometry method has a large error. Superglue can be extraordinarily accurate in rotation when textures provide strong correspondences across views, but also can fail to make inferences on hot scenes. Using attention features, our most likely camera from the camera branch substantially outperforms the previous method of associative 3D. Our optimization further improves translation substantially and rotation with small gains. In conclusion, we've presented our learning-based system to produce a coherent planar surface reconstruction from two unknown views. Future directions include using our framework to reconstruct a more complete scene with fewer frames than traditional structure from motion. Here we show examples that extend our system to more than two views by incrementally stitching new views on reconstructed views. For more information, please visit our project page. We have also released our code on GitHub. We thank Toyota Research Institute for sponsoring this research.